So we've been talking about reversible additions to carbonyls, and the third type of reaction in this category is the acetal formation. We've had the cyanohydrin formation and then gem-diol formation, and now we want to talk about acetal formation. An acetal is like a gem-diol, except the alcohols are ethers instead. And so what we can draw here as a generic mechanism is to take an aldehyde or ketone, and this time we're going to use an acid catalyst in the presence of two alcohols. And what we do is we generate an acetal functional group as our product, in which you've got two alcohols basically incorporated into that acetal. So this is the acetal, and in the process this liberates water as a byproduct. Now notice that this reaction is only acid catalyzed. The forward direction is acetal formation. Obviously, the reverse direction is what we call hydrolysis. All right, so forward direction is acetal formation, or sometimes what we call protection. Where the reverse direction, since this is a reversible reaction, is called hydrolysis, or sometimes deprotection. And that deprotection is, of course, driven by entropy. All right, so let's draw the mechanism of this reaction. And let's do this with a generic ketone. We're first going to protonate, and that protonation is going to occur at the oxygen to lower the LUMO. Okay, so we protonate. This lowered LUMO then allows us to become attacked by the alcohol. So alcohol attacks. And attacks that pi star CO. And that's going to lead to a tetrahedral intermediate. All right, then we're going to lose a proton. That loss of a proton leads you to an intermediate known as a hemiacetal. Right, and so this hemiacetal, as the name implies, is a half of an acetal, and so it has basically one R group incorporated into the structure. All right, so this is a hemiacetal. Now this hemiacetal is unstable, and so what we can do is we can undergo a protonation. Now we could protonate either of the two oxygen atoms. If we protonate the oxygen atom that formerly comes from the alcohol, we're just going to go in the reverse direction. But if we protonate the oxygen atom that is the alcohol, what we're going to get is moving forward. And so we're going to protonate this alcohol, right, to get a protonated species. What that is then going to do is it's going to allow you to have loss of water. And so the oxygen lone pairs are going to move down. Right, water's a good leaving group. And so what you're going to get is a doubly bonded system that kind of looks like a protonated system. So this is a what's known as an oxonium ion. And this oxonium ion is reactive enough, its LUMO is low enough that it gets attacked by another molecule of the alcohol, another equivalent of the alcohol. And so it's going to attack, form that tetrahedral intermediate again. and then what happens is we deprotonate one more time, and then you end up with your acetal. Right? Your acetal forms, and you get an H plus as a byproduct, and this comes from the deprotonation event that happens. So in the acid-catalyzed acetal formation reaction, the proton functioned to lower the LUMO of the carbonyl, but also to protonate the hemiacetal, and that makes water a good leaving group. And the reason this reaction cannot be catalyzed by base is because this reaction would stop at the formation of the hemiacetal. There's no way to remove the hydroxyl group. And so let's see why that occurs. And so if we had an R doubly bonded, R double prime OH plus base, that would lead us to an alkoxide. That alkoxide can then attack the carbonyl, forms a tetrahedral intermediate, and again this is under basic conditions, whereas this is under acidic conditions. And so we form a tetrahedral intermediate. We've got a new R double prime incorporated. We've got O minus there. That's then going to become protonated by grabbing the proton on one of the two alcohols. And so we have this intermediate right here. This is the hemiacetal. And then we also have the R double prime O minus, the alkoxide. But here's where the reaction stops. The reaction stops here because there's no way to remove that extra hydroxyl group. We can't protonate it because we're not under acidic conditions. We're under basic conditions. And so this forces the reaction to stop, and you can't form acetals under basic conditions. You have to form them under acidic conditions. Why would we want to use an acetal in synthesis? We want to use acetals in synthesis as protection groups. Okay, a protecting group is a way to convert one functional group into another temporarily so that its reactivity is removed and other transformations can occur. All right, so it's a way to convert one functional group into another, and the key here is temporarily, because you want to be able to remove that protecting group at the end, right? So you convert the functional group into another temporarily, so that its reactivity its inherent reactivity is removed, and other transformations can occur. Then the protecting group is easily removed thereafter. Right, so the protecting group is removed to yield the original functional group. Okay, and so the protecting group is removed easily to regenerate that original functional group, and you're able to have a new set of bonds to form. So let's take the following example. Let's take this this funky example here, in which we've got a carboxylic acid and a ketone in the same molecule, and we want to convert that molecule into the following alcohol. Okay. Note that we need to reduce the carboxylic acid without reducing the ketone. Okay. And so what ways do we know of to reduce carboxylic acids? Well, we use LAH, right? So this we can reduce with LAH. But the problem is that this ketone will also react, right? So LAH is more reactive and less selective, and so both the ketone and the carboxylic acid would be reduced to the alcohol. But what we could do is we could make an acetal out of that ketone. If we make the acetal first, the lithium aluminum hydride will only react with the carboxylic acid functional group. The acetal will remain inert, and then you can remove the acetal through hydrolysis to regenerate the ketone. And this is known as a protection-deprotection scheme. And so how would that work? Well, the first thing we're going to do is we're going to take that ketone and we're going to protect it as the acetal. So the way we protect the acetal, protect the ketone, is to make an acetal. And so what do you need for an acetal? You need some sort of alcohol, two alcohols, or a single diol. So let's say we use this diol. You need a ketone, of course, so we have that in our starter material. And then we need an acid source. We're going to use Paratoluene sulfonic acid, and so that has the structure that I'm going to show here. And this is often a very convenient acid source to use. So this is Paratoluene sulfonic acid. Its structure is very similar to Paratoluene sulfonyl chloride, so tosyl chloride that we had before. Okay, so the product of that reaction is going to be the incorporation of the two alcohols into the acetal. So our acetal carbon is that one, right? And our ketone, or excuse me, our carboxylic acid is still intact. So then we can undergo the lithium aluminum hydride reduction. So LAH, THF, minus 78 degrees, and we're going to work it up with 15% sodium hydroxide. Right, that's going to give us the reduced carboxylic acid while keeping the acetal intact. Then we need to remove the acetal. In order to remove the acetal, we need to have an acid catalyst, so let's say HCl. And now we need water as the nucleophile, because the oxygen atom of the water is going to eventually become our carbonyl oxygen again. And so we're going to have this as our product. Okay? So, just to review, acetal formation, the requirements for acetal formation are a ketone or aldehyde. We need two alcohols or a single diol. A diol, of course, has two alcohols incorporated, and then some acid source. For hydrolysis, we need an acetal, we need water, and we need an acid source. And the mechanism for this is going to be the reverse process where water is incorporated. Another use of acetal in synthesis is in the use of Grignard reagents in the presence of carbonyls or alcohols. So let's propose the following. So let's say we wanted to take that bromodiol and we want to convert it into the following structure. So we want to convert it into let's say this one. Okay. Okay, so if we treated the starter material below this starter material with a magnesium metal, the resulting Grignard reagent would immediately be destroyed by the alcohol groups, right? Because they've got protons. So what we have to do is we have to protect that diol as an acetal. So how do we do that? Well, we first convert that diol into an acetal. So we need a diol. Okay, good, we have it. We need an acid source, paratoluene sulfonic acid, and then we need some sort of ketone or aldehyde. Let's just choose acetone. With that set of reagents, what we're going to do is we're going to generate an acetal functional group. Right, so those two oxygens are going to be connected by what was formerly the acetone. So these two carbons are identical here. Then what we can do is, now we don't have any protons around, we can then treat that with magnesium metal. So magnesium metal in the first step will generate the Grignard reagent. The acetal stays as the acetal. It's completely inert. You can then react that Grignard reagent with a second stage of this reaction. Let's say we react it with benzaldehyde, and then we work it up with ammonium chloride. Okay, we're going to get nucleophilic attack of the Grignard reagent onto the pi star CO. That's going to generate a new carbon-carbon bond, and then we form this alcohol. Oops. This alcohol in which the acetal is still intact. Okay, and then what we can do is we can treat that acetal under hydrolytic conditions, so HCl and water, and that's going to regenerate your diol. And so this is another example of using acetals in synthesis. So the idea in a protection-deprotection scheme is you use some reactive functional group, you protect it as an acetal, and then you can do other chemistry which won't affect the acetal, and then finally you can reveal the original functional group back by removing the acetal to reveal either the ketone or the alcohols. Now, the most interesting example of acetals in all of chemistry is sugar chemistry or carbohydrate chemistry. So let's talk about that briefly. All right, so you might recall carbohydrate chemistry from last semester when we had these these Fischer projections. And so the Fischer projections are a nice way of drawing alcohols. Polyols, and these polyols, like this one, are sometimes used for signaling. So this is the molecule glucose. Okay, so it's important for cellular homeostasis. We draw these Fischer projections in their linear forms, but sugars have, of course, another type of form, and that's the cyclic form. But the cyclic form is just another example of an acetal. All right, so in the presence of water, these things will spontaneously cyclize. And so what you can think about is this glucose molecule has both an aldehyde functional group and it has alcohol functional groups. And so what can happen is that these can cyclize, they can react with one another to create different cyclic sugars, all right, what we call pyranoses. Okay, so one of the sugars that forms is this one here. Okay. And this sugar is called beta D glucopyranose. Okay, a pyranose is just simply a six-membered ring. Okay, this anomeric carbon right here can have two orientations for that alcohol. In the case where the alcohol is sitting in the equatorial position, we say that that's the beta version. And when this cyclizes, we get 67% of the beta version. Now, what can also happen is you can get the alpha version. So I'm going to open up this ring here. I'm going to sort of show this in a little bit different perspective. All right, so there's the alcohol. Here's that aldehyde. So this is kind of folded up a little bit. What can happen now is we can rotate around that bond so that we get the orientation of the aldehyde going down. And then we can get formation of the other anomer. Right, so the anomeric carbon here has that alcohol pointing down. And so this is called alpha D glucopyranose. And again, the glucopyranose means that it's a six-membered ring. The alpha part signifies that your alcohol is pointing down. So sugars have both the alcohol and the aldehyde functional groups, but these normally exist as these cyclic hemiacetals. And compared to acyclic hemiacetals, which we've said are unstable, the cyclic hemiacetals are completely stable, and this is how you'll often see them in textbooks. This is how they exist in your body. They exist in this cyclic form, mainly because they are six-membered rings, and we've said before that six-membered rings are the most stable type of ring that you can have.